Welcome to CMG's webinar on modeling and optimization of advanced SAGD wellbore completions. My name is Anjani Kumar. I'm the Vice President of Consulting Support and Training at CMG. I'm pleased to introduce Anson Abraham, who will be presenting today's webinar. Anson is a reservoir simulation engineer with the Consulting Support and Training Group at CMG. Anson has over 9 years of industry experience, out of which 6 years has been in SAGD and thermal processes. Prior to joining CMG, Anson has worked as a field engineer and a domain champion for design and implementation of multi-phase flow meters in SAGD operations. Over the last 2 years, Anson has developed a specialization in simulation and optimization of advanced wellbore completions using FlexWell in STARS. Anson holds a Bachelor of Science degree in Petroleum Engineering from University of Adelaide and a Master of Science degree in Geosciences and Engineering from IFP in France. Before we start the webinar, I'd like to inform you that there will be a question and answer session at the end of the webinar. So if you want to submit your questions, you can do so anytime using the chat window on the right of your screen. Over to you, Anson.
Thank you, Anjani. Hello everyone, my name is Anson Abraham, and today I'll be talking about modeling and optimization of advanced SAGD wellbore completions. In terms of agenda, today we'll cover an introduction into FlexWell, highlighting some of the features and capabilities. Then we'll go through a demo on how to set up a FlexWell model, after which I'll go through a demo on the optimization of circulation using CMOST, and finally a couple of case studies. In reservoir simulation, the traditional approach to representing wells is to use a source-sink model. Source-sink models are simplistic and they allow for quick runtimes. The primary focus in such models is always reservoir deliverability, and hence for full field applications such as history matching and forecasting, source-sink models work fine. Although they're simplistic, they've come a long way and now include gravity, friction, and heat loss calculations to some extent. They can model complex trajectories in multilateral wells also. However, they still lack the physics to be able to model the complex flow dynamics that we see in the wellbore. So why model and optimize the wellbore? It's important for us to understand the wellbore and reservoir interaction, as it can have a profound impact on the production profile. Consider undulating wells, where liquid loading and slugging or fluid segregation can have an impact on the production profile, or thermal processes where the heat transfer between tubings and the reservoir can impact the thermal process and the recovery itself. Simply put, the wellbore is the interface through which we interact with the reservoir. And hence, for us to understand it better, we need to be able to model it. And if we are able to model it, then it presents an opportunity for us to be able to optimize it. Traditionally speaking, the completion design and optimization fell within the domain of the completions engineer or the productions engineer. And we often use standalone tools to be able to do this. But we all know the heterogeneous nature of our reservoirs. And geology is something that we cannot change. We have to work around it. Some processes are more sensitive to geology than others, and hence this one-size-fits-all approach doesn't quite work. In STARS, we have a detailed wellbore simulator that is coupled to the reservoir simulators, and thus we're able to customize the well completions for the reservoir, hence maximizing the value of the asset. In STARS, in addition to the source-sink model, we also have FlexWell model. FlexWell is a discretized mechanistic wellbore model that is coupled to a reservoir model, and it models the fluid and heat flow in the wellbore and in between the wellbore and the reservoir. And within it is incorporated the physics to be able to capture the complex flow dynamics that we see in the field. FlexWell is developed to handle complex well trajectories and completions. It can handle real trajectories. So now we are able to understand how the trajectory affects the flow profile. An example would be liquid loading or fluid segregation. We can handle transient and segregated flow, and so we can model circulation and startup stages. Just as the reservoir is discretized, the wellbore is also discretized in the FlexWell. Each specified FlexWell is solved independently and is coupled to the reservoir. Just as we solve mass, energy, and momentum balance in the reservoir, we also solve mass, energy, and momentum balance equations in the well. Darcy's law dictates the flow in the reservoir, whereas pipe flow equations dictate the flow in the wellbore. As I mentioned in the previous slide, each specified FlexWell is solved independently and is coupled to the reservoir. Thus, at every time step, the wellbore is solved first, keeping the reservoir constant. Then the reservoir is solved, keeping the wellbore constant. Thus, the reservoir always lags behind the wellbore by one iteration at every time step. Frictional pressure drops are also calculated. First, the flow regime is evaluated from the gas and liquid velocities, and then the appropriate frictional drop calculation is used. This is based on the work by Khalid Aziz and Petelas. In FlexWell, the tubing and the liner sizes may be constant or variable, such as the case of tapered strings. We can model flow control devices, packers which prevent axial flow across the perforations. We can also model solid deposition initiated via reactions such as coke deposition in the case of in situ combustion projects, and this solid deposition reduces the hydraulic diameter. FlexWell is able to handle a wide variety of combinations and configurations. It can handle up to 3 tubings, one of which may be concentric, and an additional instrumentation tubing also. There's a lot of flexibility built into FlexWell which helps us replicate the wellbore into the model. This slide shows us some of the configurations that FlexWell is able to model. Often we may want to model the wellbore to surface. In doing so, there are 2 options. The first option is to use FlexWell to surface, where the overburden is explicitly gridded to surface. Or the second option is to use FlexWell in the reservoir section and semi-analytical model in the riser section. Semi-analytical model, or SAM, is another module that can be added onto a wellbore model, either SourceSync or FlexWell, and essentially calculates the pressure drop and the heat loss from the wellhead to the first perforation. Just as FlexWell is discretized, semi-analytical model is also discretized, and momentum and energy balance equations are solved for each segment. SAM uses its own analytical formation temperature and hence does not need an explicitly modeled overburden. When modeling lift mechanisms is another important aspect of the well performance. When we come to modeling pumps, there are 2 options. We can use SAM or semi-analytical model. With SAM, we can explicitly provide the pump pressure and the pump power. The second option is to use FlexWell with a withdrawal point defined at the pump location. Another very common mechanism that we use is gas lift. Once again, there are 2 methods that we can use. We can use SAM in combination with FlexWell. In this method, we can define the gas lift port locations and the gas lift rates. Or the other method is to use FlexWell all the way to surface and to model a gas injection string as one of the tubulars in FlexWell. Now that I've given you a brief overview of the features and the capabilities of FlexWell, we'll go through a demo on showing you how to set up a FlexWell model. We'll convert a SourceSync model that was set up for SAGD and convert that into a FlexWell model. We'll model both the circulation and the SAGD period. For the benefit of those who are not aware of the SAGD period, of the SAGD process, direct injection of steam into cold bitumen is not possible. We need to heat the reservoir so as to achieve the initial mobility and the initial injectivity. We do this by circulating steam in the upper injector well and the lower producer well. So in this particular example, we will model the circulation period and then switch over to the SAGD period. And for this, we'll use a dual parallel tubing configuration. However, the same logic can be applied to any tubing configuration. In the circulation period, both the upper injector and the lower producer well, we will be circulating steam. The annulus will be shut in for both the wells. We will inject in the long tubing and produce in the short tubing, and we'll model the circulation period for 90 days. When we switch over to the SAGD period, in the upper injector, the annulus will continue to be shut in, and we will inject steam in both the long tubing and the short tubing, as you can see in the schematic here below. In the SAGD period, for the lower producer well, we will be producing from both the long and the short tubing, as you can see in the schematic, and the annulus will continue to be shut in. Before I switch to Builder, I'll go through the setup. So as I mentioned, in the circulation phase, the annulus would remain shut in. The long tubing, we would be injecting in that, and we would be producing the returns from the short tubing. When we switch to the SAGD phase, the annulus would continue to be shut in. We'll continue injecting in the long tubing, and also we will be injecting in the short tubing. Hence, we need to replace the short tubing to an injector type in the SAGD period when we switch from circulation to SAGD. Replacing the well ensures that the pressure profiles and the saturations from the last time step is preserved. Now I'll switch to Builder. As you can see, in this particular model, this is a source sink model that was set up for SAGD. We already have two wells at the injector location and the producer location, and I have renamed them as injector annulus and producer annulus. In the first step, since the annulus and the tubulars follow the same trajectory, we'll copy over the annulus trajectory to create the tubulars that we require. To do that, I'll go to Well and Recurrent. I'll select the Copy Well option, and since we're going to be copying over the injector, I'll select the Injector option and Injector Annulus. We want to copy all the perforation information as well as all the geometric information. Here in this window, I'll select the option to manually enter the name of the well. And since we're going to be using the same, we're going to be using the well from day one, we'll retain the original definition date. And I'll call this well Injector Long Tubing SAGD. As you can see, I've copied over the perforations from the injector annulus to the injector long tubing SAGD. There's an exclamation mark beside it, basically telling me that we have not put in the constraints. Before I jump to do the constraints, we have to repeat the same process for the short tubing and the short tubing that we require for the circulation period as well as for the SAGD period. For the sake of time and to avoid repetition, I've repeated this process in another file, which I'll switch over to now. As you can see here, at this stage in this file, I've already copied over the annulus to create the tubulars, and we have the 3 tubulars that we require for this particular model. Let's go ahead and do the constraints first. So to do the constraints, I'll double click on the injector long tubing SAGD to open up the well events window. And since we'll be injecting in this well, we'll define this well as an injector. I'll select the O2 apply option. And then I'll switch to the constraints tab. In the constraints tab, for our constraints, we'll be injecting at a maximum of 2000 kPa. And we'll be injecting a maximum steam rate of 100 meter cube per day. Since we want any time steps with constraint violations to be repeated, I'll select the continue repeat option. At this stage, we've told builder what rate and what pressure to inject it. However, we have not told what fluid and what temperature and quality to inject at. So I'll go to the injected fluid tab, select water. As for temperature, I'll select 212.1 degrees C. This corresponds to the saturation temperature at the 2000 kPa pressure that we've specified. Now these constraints are for the circulation period. When switching over to the SAGD period, we need to inject more steam in. So I'll change the date and change the constraint to reflect that. So from the date drop-down menu, I'll select April 2008, and back in my constraint window, we'll change this to 250 cubic meter per day and apply. So at this stage, we've defined the constraints that we require for the long tubing for both the circulation stage as well as for the SAGD phase. Now we'll go to the next well, which is the producer well that we'll be using for the circulation period. We'll be producing our returns in this well, so we'll define this well as a producer well. And as for constraints, we'll select a minimum bottom hole pressure of 1800 and a maximum liquid rate of 150 cubic meter per day. Once again, I'll select the continue repeat option. The difference of 200 kPa ensures that the steam that we inject condenses in the wellbore and releases its latent heat into the reservoir. I'll select apply. At the end of the circulation period, we no longer need this well, and so we can shut the well in. So from the date drop-down menu, once again, I'll select April, and under the options tab, I'll change the status to shut in. So this way, we've shut in the well, this producer well, at the end of the circulation period. As for the short tubing that we'll be injecting steam in, and the start of SAGD, we'll change that well to injector, and we'll use similar constraints to what we used for the long tubing. So I'll come to the constraints tab, and once again we'll be injecting at 2000 kPa, and we'll be also injecting 250 cubic meter per day of steam. Once again, we've told builder what rate and what pressure to inject at, but we've not told it what fluid. So we'll come to the injected fluid tab, and here select water. As for temperature, 212.1, that corresponds to the saturation temperature at the 2000 kPa pressure, and 90% steam quality. And I can say OK. So at this stage, we've defined all the constraints that we require for the upper injector well. Now we'll jump in to define the flex well. To define the flex well, I'll double click on the flex well button here. Since we're creating a new flex well, I'll click on new flex well, and we'll change the name. And I'll call this well injector flex well. We want this flex well to be active from day one. so I've retained the original definition dates. We won't be modeling any solid deposition in this case, and the autocomplete perforations option ensures that that for a tubing the discharge happens only from the toe. At this stage, you can see from the schematic here that an annulus has been created. Now we need to assign a well to this annulus. So from the well drop-down menu, I'll select injector annulus, and I've selected, now I've assigned injector annulus as my annulus. If we wish to change the thermal properties, we can do so in this section here. The casing is going to be a 9 5/8 casing, so we'll change the diameters accordingly. If you wish to use a variable diameter or a tapered string as such, we can select the variable option and then enter the diameters accordingly. We're using a 9 5/8 casing, so the wall ID is going to be 8.921 inches. And the wall OD is going to be 9.625 inches. And we can apply. So now we've defined the annulus and the dimensions of the annulus. Now we can add a tubing to it. So we'll select the Add Tubing option. And as you can see from the schematic, a tubing has been added. Similar to before, we'll assign a tubing to this FlexWell tubing. So we'll select the injector long tubing SAGD and assign it to that well. Once again, if you wish to change the thermal properties, we can do so here in this section. For this well, the long tubing is going to be a 3.5-inch tubing, so the ID is going to be 2.99 inches, and the wall OD is 3.5 inches. If we wish to add a concentric tubing, I can click on the Add Concentric Tubing option. But since we're going to be working with a dual parallel tubing option, I'll come back to the annulus tab and add another tubing. And as you can see from the schematic, it reflects a dual parallel tubing configuration. Once again, we'll assign the well to the tubing. So we'll select the short tubing circulation. And this is going to be a 4.5-inch tubing. So the inner diameter is 3.96 inches and the outer diameter is 4.5 inches. So at this stage, we have assigned the wells to the FlexWell. Just as we have well events, we also have FlexWell events. I'll click on the Events button on the model tree view there. And you can see that this FlexWell was activated on 1st of Jan. The annulus is shut in. We are injecting in the long tubing and producing from the short tubing. When switching over to SAGD phase, we need to replace the short tubulus, so we'll do that now. We'll be switching over in April, so in the April date under FlexWell event, I'll select Replace, and we'll select short tubing SAGD and apply. So at this stage, we've replaced the short tubing, the injector type well with the producer well. Finally, we also have to change the landing depth. So we'll go to the short tubing, and here under the select completion branch perforation length, I'll select Edit, and we'll change that to 150 meters. And I'll apply. So at this stage, we've completed the setup of the FlexWell, of the injector FlexWell. We can repeat the same process for the producer well as well. Once again, for time, as a time-saving measure and to avoid the repetition of the steps. I've done this already in another file. As you can see, in this model we have 2 flex wells and we have 8 wells. So we've repeated the same process as I've shown for the injector well with the producer well as well. Now I'll switch back to the PowerPoint presentation. Now that I've shown you how easily you can set up a FlexWell model, we'll go through a quick demo on the optimization. As we all know, the circulation period is an operationally expensive period where we are injecting steam with little or no oil returns back. The longer the circulation period, the more delayed the cash flow. Hence, we want a circulation period that is efficient, but we want it short as well. So in this next step, in this next demo, I will show you an optimization workflow where we'll optimize the circulation period based on the back pressure, or in this case, translated to as a delta pressure between the long tubing and the short tubing, the absolute injection pressure, and the duration. In order to evaluate the most optimal case, we'll look at the cumulative oil produced at the end of 1 year of SAGD. And we'll also monitor the average sector temperature between the wells. To do this, we'll be using CMOST. CMOST is a CMG suite that allows us to do sensitivity analysis, assisted history matching, optimization, and uncertainty analysis. CMOST uses a master data set or a CMM file to specify the parameters to be altered. Essentially, it's a template file wherein we can specify where it will be generated based on where new data sets will be generated based on the various combinations for the parameters that we have selected. The CMM file can be created manually using a text editor, through CMOST with a CMM editor, or through Builder. Now I'll jump into CMOST. As you can see here, I've already created a study where I've put in the general information. The next step in this workflow is to define the parameters. I'll click on the parameterization and expand on the parameterization option. I'll click on the parameters to add the parameters. And the first step is to add the delta pressure. So here I've created a new variable called delta pressure, and I've assigned it as a discrete real option, and I've created different values varying from 25 to 200 kPa. The next step is to assign the injection pressures for the long tubing. So to do that, I'll go to the Builder option, and as you can see, now Builder opens up with the CMOST definition window. Just as we have a model tree view in Builder, we also have a model tree view in CMOST, the CMOST window. We'll expand on well and recurrence, and we'll expand on wells. Once again, I'll expand on events and constraints. Since we're going to be varying the absolute injection pressure, I'll select the injection long tubing SAGD, and we'll be changing the bottom hole pressure, so I'll add that to the list of parameters. And here I'll change that as, I'll rename the parameter as injector long tubing SAGD. Similarly, we also want to be varying the short tubing pressure, so I'll select the injector short tubing circulation, and I'll add the bottom hole pressure associated with that to the parameter list. And once again, I'll rename this as injector short tubing circ. So now at this stage, we've defined the injector long tubing SAGD and the injector short tubing circ pressures as my parameters to change. We'll also add the producer long tubing injection pressure, so I'll select the producer long tubing circ and add that to the parameter list as well. And we'll call this injector long tubing circ. Similarly, we also will do the back pressure on the short tubing for the lower producer well. So I'll select the producer short tubing and the bottom hole pressure associated with that. We'll add that to the parameter list as well. And I'll call this producer short tubing SAGD. We can save the changes and I'll click OK to return back to CMOST. Now that we're back in CMOST, I can click on the import button to import all the variables that parameters that we've created. As for the injector long tubing SAGD, we'll select the discrete real option and we'll vary the pressure from 1500 kPa to 2500 kPa with pressure steps of 500 kPa. Now we want the short tubing pressure to be controlled by the delta pressure. So for the short tubing circ, we'll select this from source, we'll select the formula. In the formula option, we can use a simple, I'll use a simple JScript code, or we can even use complex Python or JScript codes to use in this particular case. I'll write a simple formula where I'll say injector long tubing SAGD minus delta pressure. This way, when CMOST generates the set template files, the injector short tubing's pressure is always linked to the injector long tubing pressure via the delta pressure. We can repeat the same process for the producer SAGD well as the producer short tubing as well. Once again, for the sake of time, I've done this step already, and I'll switch over to another CMOST window. As you can see, I've already created the steps, recreated the steps in CMOST. The next step is, so at this stage we've done the delta pressure and the absolute injection pressures. Now we'll do the duration. To do the duration, I'll click on the edit button. It'll bring up my CMOST CMM editor, and I'll search for start SAGD as I've commented it out there. And this date here relates to the start of SAGD period, so we'll create this as a different parameter. So I'll highlight the date and right click to create a parameter, and I'll call this duration. Now for duration, we'll select the discrete text option, and we can have different dates varying from 2 months all the way to 5 months. For the sake of time, once again, I've already done this step in another file, so I'll switch over to the next file here. As you can see, here I've created the duration parameter and I've assigned values to it. At this stage, we've defined all the parameters, and we'll define the objective function. Now, as I mentioned, the objective function is going to be the cumulative oil produced at the end of 1 year of SAGD. So under my basic simulation tab, I'll select under Objective Function, I'll select the Basic Simulation Results tab and click on Insert to add a new parameter. And we'll call this QMOIL. And under Origin Type, I'll select Sector. And we'll look at the cumulative oil produced at the end of 1 year of SAGD. So at this stage, we are ready to launch, we are ready to generate the experiment. So I'll go into the Experiments table and click on the Generate Experiments tab, and we'll use all the parameter combinations to generate the design. So as you can see here, CMOST has generated a whole bunch of data sets, varying the different parameters with the different combinations. At this stage, we can run we can launch CMOST to run the data file. I'll switch over to the presentation and go over the results quickly. As I mentioned, we need to ensure that the circulation is short as possible but efficient as well. By running the CMOST the optimization on the circulation period, we were able to reduce the circulation period by 2 weeks. The base case had an injection pressure of 2000 kPa, while the optimized case came up to 2500. And the duration went from 90 days to 75 days. This means that we have positive cash flow a little earlier. In the next section, I'll talk about modeling of flow control devices. We all know flow control devices are basically used to specifically inject steam at certain points along the well. This results in a more uniform and a controlled steam chamber growth, essentially a better utilization of steam, and which translates to a lower steam oil ratio and lower operating expenditure. CMG has worked closely with the industry to implement flow control devices into FlexWell. Weatherford's GDA and Baker's equalizer tools are some of the FCDs that can be simulated in STARS using FlexWell. Currently in STARS, the built-in equations to model the orifice, friction, and venturi devices are already there. In addition, we can also use FCD table format. This is a simple format that's able to model all the types of FCDs that's available in the market. Essentially, it's a delta pressure versus flow rate table that defines the behavior of the flow control device. Pressure or volumetric flow rate can be defined as a dependent variable. In the upcoming release, we can also use mass rate or molar rate instead of volumetric flow rate. Additionally, we can also have optional dependencies such as gas mass fraction, inlet pressure and temperature, or water cut as well. Now we'll go through a couple of case studies that highlight the benefits of using an integrated approach to optimizing completion design. The first case study was undertaken by CNRL, and the details can be found in the SP paper mentioned. This is quite an interesting case. As you can see, in this slide here, you can see the 2D slice of the reservoir. There's low sealing around the heel, good quality sand in the middle, and relatively good but thick pay near the toe. So in this case, the authors had to customize the well completion to address this heterogeneity that we see in this section. The conventional design was to use a dual tubing injector and a single short string producer. As we can imagine, the conventional design would inject more steam to the heel, and steam breakthrough became a major concern because of the low sealing near the heel. To test out another theory, the CNRL decided to use a 4.5-inch long string instead of a dual completion string, and inserted steam splitters in different locations. The objective was to change the pressure profile within the injector, and as we know, pressure profile within the injector liner is a reflection of the steam rate into the wellbore, into the reservoir. On the left, you can see the pressure profile and the injector liner for a standard configuration. As we expect to see, it's highly skewed towards the heel. Whereas by using steam splitters, we are able to drastically change the pressure profile and ensure that it's more skewed towards the toe. Two steam splitters were installed at 500 meters and 750 meters with an open toe. This meant that about 50% of the steam went to the toe and 50% between the two splitters. The bottom right chart shows the steam rate along the wellbore. The red represents the standard configuration and the blue represents the steam splitter configuration. As we can imagine, with the standard configuration, steam is injected more in some locations and very little in other locations. Whereas by using a steam splitter, we are able to distribute this much better. So now, having understood that and moving on to the producer liner, the authors decided to test the scab liner theory. As you see in this chart, chart A shows the profile with no scab liner, and charts B, C, and D shows with increasing scab liner diameters. As you can see, increasing the scab liner diameter skewed the profile closer towards the toe. As we see in this case, we needed the area around the toe to be more heated. So based on the pressure profile and the studies that they've conducted, they realized that the desired profile should look something like the dotted line that you see in green. Using steam splitters and scab liners, they were able to replicate that, and obviously that showed in the results as well. As you can see, the scab liner with the steam splitter is much higher than the base case. Thus, by taking an integrated wellbore approach, the authors were able to customize the completion design to address the geological heterogeneity that they had in the reservoir. The next case study was conducted by Weatherford, and it was investigating the flow control devices on the overall SAGD process. This case study was done in two phases. The first phase was the sensitivity analysis, where the authors looked at the number of FCDs, location of FCDs, and the properties of the flow control devices, and the second stage was optimization. The conventional design, or the base case for this model, was with an injector well with a stringled 4.5-inch long tubing and a producer with a scab liner. As you can imagine, this promotes the steam growth closer towards the toe of the well pair. In the first phase of this sensitivity analysis, the authors looked at the total number of FCDs in the injector well. As we can see on the left, there was insufficient heating of the reservoir near the heel in the base case, but by adding flow control devices, they were able to improve the steam chamber conformance, as you can see on the bottom left. This also reflected on the cumulative oil produced. The authors also conducted a sensitivity on the location of the flow control devices and the properties as well. However, because of manufacturing limitations, the properties of the flow control devices was not taken into account for the optimization cases. Moving on to the producer FCD sensitivity studies, the authors found that steam breakthrough was mitigated by using production FCDs. However, it had minimal or no impact on steam oil ratio and oil rate. Thus, taking all of this into consideration, they devised a workflow. The authors started with a geological model, built a reservoir simulation model, and coupled FlexWell to it. Then they ran the optimization on the number of FCDs and the location of FCDs, following which the optimization was done on the number of ports. This was done on the injector first and then on the producer. On the injector well, as you can see, first the authors optimized the number of FCDs and the locations of FCDs. The optimal case is case 4, and as you can imagine, this promotes the steam chamber growth closer towards the heel. The overall result or the impact of this optimization was 126% increase in NPV. In the next step, the authors took the same optimization workflow to the producer FCDs. This time the FCDs were distributed. The optimal solution was to distribute the FCDs evenly along the scab liner. And eventually the final result was that the cumulative oil went from about 150,000 to about just under 300,000. Similarly, the SOR also reduced from about 3 to about 2.1. The total impact in terms of NPV was 146% increase in NPV. It went from about 30 million to about 79 million, as you can see on this chart. Thus, by taking an NPV-based workflow and coupling it with a wellbore and reservoir model, they were able to optimize the well completions to maximize the value of the asset. Here are some additional resources that you may want to look upon, and this basically looks at using FlexWell to optimize the work completion design and the operating strategies. Finally, in conclusion, FlexWell, we know that we provides the capability to model complex wellbore completions while being coupled to the reservoir simulation model. This helps us understand how the wellbore hydraulics affects the recovery, and we are also able to optimize the well completions and improve the value of the asset. With this, I conclude my presentation. I'll pass it on to Anjani.
Thank you, Anson. We'll now open up the floor for questions. If you have not already submitted your questions, you can do so now using the chat window on the right of your screen. Time permitting, we will try our best to take up as many questions as possible. If we are unable to do so, then one of our CMG representatives will get in touch with you individually and discuss your questions. So the first question that I can see here is from Mehdi Shams, and he's asking, can we use FlexWell to put packers and ICDs in the SAGD well, or ISEG well is the only way to define that?
We certainly can use packers and ICDs in FlexWell. FlexWell has the capability to be able to model that isolation. So yes, we can certainly model that with FlexWell.
The next question is from Afwerki, and he'd like to know, if we use bullheading, how would we configure FlexWell and how do we optimize it in CMOST? And at the same time, he's using pumps to produce back.
In this scenario, once again, it's we can use to be able to model the pumps. We have two options. We can use SAM, which will model the lift capabilities. As for the bullheading exercise, we certainly can vary it based on the steam quality and the injection pressures. Obviously, there's this level of uncertainty involved in this, considering the saturation profile and such around the wellbore, so that needs to be accounted for.
And just to add to that, I mean, in terms of the wellbore configuration, you'll set up the FlexWell exactly to mimic the wellbore configuration that is in the field, and you can certainly use CMOST to optimize the injection pressure, the duration of bullheading, and things like that. So definitely CMOST has the potential to optimize the bullheading process as well. The next question is from Ethan, and he'd like to know, if solid deposition option is checked in FlexWell, does it use reaction expressions defined in Builder to do so?
Yes, we have to define, to be able to use a solid deposition option in FlexWell, we need to already have the reactions defined in Builder under the fluid component section.
The next question is from Muhammad, and he'd like to know, can we discretize wellbore for FlexWell differently than reservoir discretization?
FlexWell uses the same level of discretization as the reservoir. Essentially, the FlexWell is coupled to the reservoir, and hence it uses the same level of discretization. If we need to go finer with the FlexWell, then we need to go finer with the reservoir as well.
The next question is from Don Mims, and he'd like to know, can we track the steam quality of injection along the length of the well completion?
Absolutely. We can track the steam quality, pressure, temperature, and the saturation of the different phases as well.
The other question is from Jeremy, and he'd like to know, can we do steam flashing calculations inside FlexWell?
Absolutely. That is accounted for by inherently within the model. Any phase changes and composition changes is already accounted for. So yes, we are able to handle the steam flashing within the wellbore.
The next question is from Fernando, and he'll like to know, can we use FlexWell to model in situ combustion? Do you recommend to use the FlexWell to represent ignition process? Definitely you can use FlexWell to model the in situ combustion process, because there are different reactions that can happen in the in situ combustion process, either in the reservoir or in the wellbore. So definitely the ignition process can be modeled using FlexWell. If you inject air in the wellbore, you have to be careful whether there is oil present in the wellbore or what kind of fluid is present in the wellbore, and how the injected air reacts and responds in presence of the fluid present inside the wellbore. As well as if there is coke deposition happening inside the wellbore, then definitely there will be a reduction in the hydraulic diameter of the wellbore, and definitely FlexWell can model all of those. The other question is again from Don Mims, and he'll like to know, have you looked at impact of distance between injector and producer? Does it differ from what we hear from literature, that is 5 meters?
We have looked at the impact on that, and it varies from case to case, varying from the depending on the reservoir heterogeneity and such. So it's something that we have to look on case by case basis.
The next question is, can we put in heaters in FlexWell?
Absolutely. There is a new option that allows us to put a heater cable within FlexWell, so we are able to provide electrical heat or so as such within FlexWell.
Question that's on the screen here is from Roger, and he'll like to know is how to accurately predict the heat losses in the wellbore to the formation and heat losses to the overburden and underburden during steam injection. More precisely, is it an analytical model or is it a fully numerical model?
In the FlexWell model, the heat transfer is a numerical model. However, in the semi-analytical or SAM model, the approach is an analytical model.
And also, in order to calculate the overburden and underburden heat losses, it is an analytical model that is coupled to a fully numerical heat loss model in the grid block. The next question is, in STARS, did you solve the diffusivity equation for heat transfer in the vertical direction, or did you implement the initial temperature distribution during geothermal gradient?
So in this in STARS, we can use the with the FlexWell model, we can use the diffusivity equation to be able to model it. If we were to use the if we were modeling the wellbore all the way to surface, then we can use the geothermal gradient and assign specific temperature values and heat losses accordingly to that model as well.
The next question is from Mike, and he'll like to know, have you tried this on deviated cyclic steam wells accounting for gas lift by steam flash in the wellbore?
Yes, we have.
And some of our clients have actually tried this, taking the FlexWell all the way to the surface, and have tried to model steam flashing into the wellbore and also gravity separation process inside the wellbore, and FlexWell is able to handle all of those mechanisms. So the next question is the diameter, and the next question is from Astrid here, and he will like to know the diameter of the annulus tubing have to support the diameter of the 3 tubings in the circulation and SAGD.
Yes, obviously the diameter, we have to ensure that the tubings that we assign will fit into the diameter of the annulus.
The next question is from Ayodele, and he'll like to know what's the difference between the intelligent segmented well and the flex well, and when do you use the intelligent segmented well? The main difference is actually gravity segregation process, because flex well is a fully numerical transient simulator, whereas a segmented well is a steady state simulator. So in a steady state simulator, you cannot model transient effects, gravity segregation. It's more of a homogeneous mixed flow in a segmented well. So if you are looking at initialization of wells where you expect a lot of transient effects, then you should be using a fully transient wellbore model, which is flex well. The next question is from Wang, and he'll like to know where is the BHP reference to the long tubing inside the injector flex well during SAGD period.
The BHP, the reference point for all the constraints that we apply for the flex well is for an injector well, it's the entry point, and for the producer well, it's the exit point. Essentially, it's the keel location if you were to model the, if you were looking at the horizontal well, or the first perforation if it's a vertical well.
The next question is from Sunil, and he'll like to know, is this for a cyclic SAGD option, or can this be used for continuous SAGD, where you have both injection and production simultaneously?
Yes, we can apply the same workflow for a cyclic SAGD option as well.
The next question is from Anuj, and he'll like to know, will FlexWell option be available in GEM and IMEX? At the moment, we don't have a FlexWell option in GEM and IMEX, and definitely if there is sufficient interest from the industry, we can accommodate that request. But as of now, the FlexWell option is not available in GEM and IMEX. The next question is, how much runtime is increased if we use FlexWell option? And this question is from Carlos.
That's a tricky one to answer because it varies quite a bit. As you can imagine, FlexWell, because it's modeling the complex wellbore flow dynamics that we see, it can vary greatly depending on the flow dynamics.
And it also depends on the complexity you're trying to model. If there is a lot of transient effects, wellbore and reservoir interaction, if the wellbore is mimicking a complex flow regime, then definitely it takes a lot more time to solve the wellbore in conjunction with the reservoir, because there could be a lot of interaction between the wellbore and the reservoir. So it's very, very case specific. The next question is from Nicholas, and he'll like to know, have you checked the tolerances of these models with reality?
Yes, we've gone through some validation processes, and we have independently done it, and I have a few backup slides to highlight that. So this was a case study that was done by CMG Foundation, which is an independent foundation that's run out of the University of Calgary. And here you can see that the dotted lines, the dots basically represent what the FlexWell is predicting versus another model that the research group came up with. So as you can see, they're pretty close in this, pretty close in terms of results. And also we have validated it against CFD, other CFD simulations as well.
Okay, so the next question is, how difficult is it to simulate FlexWell to surface? What kind of challenges are involved? And this question is from Mariam.
Simulating, in terms of setup, to be able to simulate the FlexWell to surface, it's quite easy, and it's the same process in itself as I showed in the demo. In terms of the challenges involved, obviously, because now we're dealing with vertical flow and fluid segregation as such. The flow regimes are quite different than what we encounter in the horizontal section. So in terms of run times, it does go up a little bit, but it's certainly something that we very often do, and we are able to handle that.
In terms of challenges also, since you're taking the flex well all the way to the surface, it will be modeling gravity segregation and frictional and pressure losses and heat losses along the vertical section as well. So if the well is having a lift issue, then you will have to implement artificial lift methods and things like that. So all those need to be considered while modeling flex well to the surface, because you are modeling the riser section in the well bore. The next question, and probably this is the last question for time's sake, is how do you do SAGD optimization if you don't have a CMOST package? Probably I'll take that question. Is CMOST actually facilitates optimization process by varying different parameters in an optimization scheme, and it definitely makes the whole process a lot easier in terms of automating the optimization process. If you don't have CMOST, then definitely you'll have to do it manually, generate all the runs with different parameters, design your experimental design matrix manually, launch all of those runs manually, interpret all of those runs manually, and then do some kind of a Monte Carlo simulation in terms of assessing the uncertainty. Or if you're doing the optimization, you'll have to calculate the net present value and things like that manually. So definitely CMOST is a package that automates all of these things and gets the results in a very quick way, and the turnaround time for optimization process is significantly reduced. I think we have run out of time for our presentation. There are several questions that I can see on the screen that are coming up. Unfortunately, we are unable to take on any more questions now, but definitely one of our representatives will get in touch with you and discuss with you regarding your questions individually. Again, I hope that you got a better understanding of advanced wellbore modeling capabilities using FlexWell in STARS. If you have any more questions regarding today's discussions and presentations or any other CMG offerings, then do not hesitate to contact us at sales@cmgl.ca, and one of our sales or account managers will be more than happy to help you. If you want to know more and detailed feature capabilities and advanced wellbore modeling capabilities, then definitely you can attend one of our training courses that we offer at various locations in CMG. We have the advanced wellbore modeling training in STARS that are offered from our Calgary and Bogota offices. Apart from that, we do a lot of company-specific training and customized training on a variety of subjects, and you can find those on our website. I'll invite you to check out our website at cmgl.ca/training, and there is a training calendar and a schedule on a variety of subjects. Before we conclude, I'd also like to let you know that today's proceedings have been recorded and will be posted on our website within 24 hours. You can use your CMGL credentials, that is the username and a password, to log in and access that material. So again, thank you all for joining us on today's webinar on advanced modeling and optimization of advanced SAGD wellbore completions, and thank you again.